Next chapter, Trigonometric Ratios. Trigonometry is a branch of mathematics that studies the relationships between lengths and angles of triangles. In this first part of trigonometry, we are going to look at the relationship of sides and angles in a right-angled triangle. But first things first, let's look at the parts of a right-angled triangle. And so here we have a right-angled triangle, and we know it is right-angled because this angle at C is 90 degrees. Directly opposite this 90 degrees angle, this side is called the hypotenuse. Then, if you are looking at this angle at A, this side is called opposite. It is opposite to angle A. Then this side here is adjacent to angle A. If we are looking at angle B, we will name the sides with respect to that angle. Hypotenuse doesn't change, it's always opposite to the 90 degrees angle. But now, the opposite side is the one opposite to the angle in question. This is the opposite side with respect to angle B. That means this is the adjacent side. In the 3rd century, astronomers first noticed that the length and sides of a right-angled triangle and the angles between these sides have fixed relationships. And so if we know the length of one side and at least one of the acute angles, we can find all the other sides and angles. Trigonometric ratios provide the relationships between the sides and angles of a right-angled triangle. There are 3 trigonometric ratios: tangents, sines, and cosines. Tangent of an angle. The ratio of the opposite side to the adjacent side of an angle is called the tangent of that angle. Mathematically, we say tan theta is equal to opposite over adjacent. And so in this triangle, tan theta is equal to BC over AC. Mathematical tables of tangents give the tangents of angles from 0 to 90 degrees. The tangents increase as the angles increase. Let us see how we read these tables. The tables look much like the other tables we've seen before, with 3 main divisions. First, we have the theta column, indicating degrees in whole numbers from 0 to 90 degrees. The next group of 10 columns provide the decimal degrees from 0.0, 0.1, 0.2, all the way to 0.9. But above it, we have minutes, 0 minutes, 6 minutes, 12 minutes, and so on, lining up perfectly with 0.0 degrees, 0.1 degrees, 0.3 degrees, and so on. If you recall, angles are measured in degrees and minutes. 1 degree is equal to 60 minutes, and that's why 0.1 degrees is equal to 6 minutes, 0.2 degrees is equal to 12 minutes, all the way to 0.9 degrees equal to 54 minutes. The column of differences only works for angles in degrees and minutes. For angles in degrees only, these tables can be read only up to 1 decimal place. We read the tables the same way. For example, tan 45.7 degrees. 45 is here, meets with 0.7 here, and the number is 1.247. Notice that 45.7 is the same as 45 degrees and 42 minutes. Tan 38 degrees and 36 minutes. 38 degrees is here, and 36 minutes is here. They meet here, and the number is 0.7983. What of 28 degrees and 50 minutes? We can read 28 degrees, but 50 minutes? No. This time we go to the differences group of columns. Notice that this group has only 5 columns. 50 minutes lie between 48 minutes and 54 minutes. In between the two, there are 5 minutes. That is 49, 50, 51, 52, and 53. So what we do is read the number at the lower side, that is at 48 minutes, and that tangent is 0.5498. But we had 50 minutes. 50 minutes minus 48 minutes is 2 minutes. So we go to the differences group of columns and to the column of 2 minutes. We read the coinciding number. It's 7. We add it to our previous reading. So 0.5498 plus 0.0007, that gives us 0.5505. And so tan 28 degrees and 50 minutes is equal to 0.5505. And back to our triangle. When the angles are known, we use the tables of tangents to find the ratio of the sides. For example, find the length PQ. We have tan 40 degrees is equal to PQ over 15. And so PQ is equal to 15 times tan 40. From the tables, tan 40 is equal to 0.8391. And therefore PQ is equal to 15 times 0.8391, and that gives us 12.6 centimeters. Also, if you are given the sides, you can find the angle. Let us have this triangle, and I want us to keep this triangle throughout this video. The first thing you notice is that this triangle is a real one. What I mean is that these lengths have not been chosen randomly. They can actually produce a true right-angled triangle because it obeys the Pythagoras theorem. 6 squared plus 8 squared is equal to 10 squared. And so if you made this length 9 centimeters, such a triangle cannot exist because it will not obey the Pythagoras theorem. Let us find angle theta. Tan theta is equal to 8 over 6, that is opposite of adjacent. Tan theta is equal to 1.3333. And now we need to find the angle whose tangent is 1.3333. We call it the inverse of tan theta. So we write tan inverse of tan theta is equal to tan inverse of 1.3333. To find the angle, we just reverse what we did. From the table, we look for 1.333, or if it's missing, we look for the nearest smaller number. From the tables, the nearest number appears to be 0.3319, and that matches with 53 degrees and 6 minutes. But we had 1.3333. We get the differences between the numbers. 1.3333 minus 1.3319 gives us 0.0014. We go to the differences column and look for 14, or the closest number. There's no 14. There is 10 and 15. 15 is closer to 14, and it is found in the column of 2 minutes. So we add this to our previous angle. So 53 degrees and 6 minutes plus 2 minutes give us 53 degrees and 8 minutes. And that is the angle. The next thing I want to do is find the angle at B. And I want us to have a predetermined answer so that we can test the truthfulness of these ratios. We know that the sum angles of a triangle is 180 degrees. We already have 90 degrees and 53 degrees and 8 minutes. So what is remaining? 180 degrees is the same as 179 degrees and 60 minutes. That will allow me to subtract the minutes. Of course, 60 minutes is 1 degree, so that will make it 180 degrees. And so 179 degrees and 60 minutes minus 90 minus 53 degrees and 8 minutes give us 36 degrees and 52 minutes. And so we expect that angle after we calculate using tangents. Let's proceed. Tan theta is equal to 6 over 8, that is opposite over adjacent. 6 over 8 is equal to 0.75, so tan B is equal to 0.75. Tan inverse of tan B is equal to tan inverse of 0.75. Tan inverse of tan B is B, so we find the tan inverse of 0.75. To the tables, the nearest number is 0.7481. This is the tangent of 36 degrees and 48 minutes. We subtract 0.7500 minus 0.7481 will give us 0.0019. So we look for 19 in the differences group of columns. It's there on the column of 4 minutes, so we add to our angle. 36 degrees and 48 minutes plus 4 minutes gives us 36 degrees and 52 minutes, the same angle we had calculated. Fantastic! We will keep this triangle and pretend we don't know these angles when we look at sines and cosines next. But first, let us see the application of tangents. You are looking up at something. This is called the angle of elevation. The angle of elevation denotes the angle from the horizontal upward to an object. So the angle is above the horizontal. Or maybe you are looking down at something. Straight ahead is the horizontal. And if you are looking below or downward, this will denote the angle of depression. And now we have two parallel lines and a transversal cutting across each line. It should be rather obvious really that the angle of depression is alternate to the angle of elevation, and so they are equal. Let's take an example. A bird is sitting on top of a post that is 8 meters tall. The bird spots a worm on the ground at an angle of depression of 30 degrees. That bird is a genius. How far is the worm from the base of the signpost? That's the signpost and the bird, 8 meters high, and sees a worm, and the angle of depression is 30 degrees. So how far is the worm from here? This can be depicted by a right angled triangle. This is the horizontal, and this angle is 30 degrees. The angle of depression is equal to the angle of elevation. And so we find x. 8 meters is opposite to 30 degrees. And so tan 30 is equal to 8 over x. Cross multiplication, x times tan 30 is equal to 8. We divide both sides by tan 30. Tan 30 is equal to 0.5774 from the tables. So we have 8 over 0.5774. We go to the logarithm tables. You have numbers and their logarithms. The log of 8 is 0.9031. The log of 0.5774 is 1 bar, 0.7614. We are dividing, so we subtract the logs, and we shall have 1.1417. We find the antilog of that. Log inverse of 1.1417 is equal to 13.86. And so the distance of the worm from the foot of the post is 13.8 meters. Next, ratios, sines. The ratio of the opposite side of an angle to the hypotenuse of a right angle triangle is called the sine of that angle. And so sine theta is equal to opposite over hypotenuse. Again, we have the tables of sines of angles between 0 and 90 degrees. The sines of angles increase from 0 to 1 as the angle increases. The sine of 0 degrees is 0 and that of 90 degrees is 1. The tables are read the same way as those of tangents. Let's go back to our triangle. We know these two angles, but we will remove them and see if we can reproduce them using sine instead of tangent. Angle A, sine A is equal to opposite over hypotenuse, 8 over 10, and that gives us 0.8. Sine inverse of sine A is equal to the sine inverse of 0.8. Sine inverse of sine A is equal to A. Sine inverse of 0.8, we go to the tables of sines. 0.8 is not there. The closest smaller number is 0.7997, and that is the sine of 53 degrees and 6 minutes. What is the difference? When we subtract that, we get 0.0003. We look for 3 in the difference group. It's there and at the column of 2 minutes. So we add 2 minutes to our previous angle. 53 degrees and 6 minutes plus 2 minutes will give us 53 degrees and 8 minutes. I believe this was the angle we had. Now to B. Sine B is equal to 6 over 10. That gives us sine B is equal to 0.6. Sine inverse of sine B is equal to the sine inverse of 0.6. B is equal to, we go to the tables. 0.6 is not anywhere. The closest small number is 0.5990, and that's the sine of 36 degrees and 48 minutes. The difference, it gives us 0.0010. So we look for 10 in the differences group of columns. Again, it's not there, but we have 9. This lines up with the column of 4 minutes. So we add that to 36 degrees and 48 minutes, gives us 36 degrees and 52 minutes. And so we are back to our angles. We take an example. Find the length MO. MO is opposite to the angle 38 degrees. The hypotenuse is 8 meters that we are given. And so sine 38 degrees is equal to MO over 8. Cross multiplication. MO is equal to 8 times sine 38. Sine 38 is equal to 0.6157. And so 8 times 0.6157. We go to logarithms. The log of 8 is 0.9031. The log of 0.6157 is 1 bar 0.7893. We are multiplying, so we add the logarithms. That will give us 0.6924. The antilog of that is 4.924 meters, and that is the length MO. Lastly, cosines of angles. The ratio of the adjacent side of an angle to the hypotenuse of a right angle triangle is called the cosine of that angle. And so cos theta is equal to adjacent over hypotenuse. The tables of cosines give cosines of angles between 0 and 90 degrees. But unlike tangents and sines, cosines decrease as angles increase. Cos 0 is equal to 1 and cos 90 is equal to 0. The values in the differences column are subtracted and not added. Back to our triangle, we find the angles using cosines now. For A, Cos A is equal to adjacent over hypotenuse, 6 over 10, and that gives us 0.6. And so cos A is equal to 0.6. Cos inverse of cos A is equal to the cos inverse of 0.6. A is equal to, we go to the tables. 0.6 is not there. The nearest small number is 0.5990. This is the cosine of 52 degrees and 12 minutes. The difference, we get 0.0010. We go to the differences columns and look for 10. It is not there, but we have 9. This is under column 4 minutes. We subtract this from our angle. 53 degrees and 12 minutes subtract 4 minutes will give us 53 degrees and 8 minutes. And this was the same angle we had. For angle B, cos B is equal to 8 over 10. Cos B is equal to 0.8. Cos inverse of cos B is equal to cos inverse of 0.8. B is equal to, we go to the tables. There is no 0.8, we have 0.7997. This is the cosine of 36 degrees and 54 minutes. We write that. The difference we subtract, we get 0.003. We look for 3 in the differences columns. It is here under the column of 2 minutes. We subtract that. 36 degrees and 54 minutes subtract 2 minutes gives us 36 degrees and 52 minutes, and we are back to where we started. An example, find the length x. In the solution, cos 60 degrees is equal to 6 over x. That is adjacent over hypotenuse. Cross multiplication, x times cos 60 is equal to 6. We divide both sides by cos 60, and x is equal to 6 over cos 60. Cos 60 is equal to 0.5, and therefore 6 over 0.5 gives us 12, and so x is 12 meters. And so in summary, this is a right-angled triangle, and I know that because it has a right angle here. This box denotes that these two sides of the triangle are perpendicular to each other. The side across the right angle is the hypotenuse. And if I had angle A here, this side is adjacent to the angle A, and this side is opposite to angle A. Here are the trigonometric functions. Sin A is equal to opposite over hypotenuse. Cos A is equal to adjacent over hypotenuse. And tan A is equal to opposite over adjacent. An easy way to remember that is to use the 3 words SOHCAHTOA. It's just a way to help you remember that sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Next, we look at the relationship between the trigonometric ratios of complementary angles. Now consider the right angle triangle PQR. In this triangle, theta plus alpha is equal to 90 degrees. Why? Because the sum angles of a triangle is 180 degrees. We already have 90 degrees at R, and so what remains is 90 degrees. And so angles theta and alpha are complementary angles. That is, they add up to 90 degrees. Therefore, alpha is equal to 90 minus theta. Sin alpha is equal to PR over PQ, and cos theta is equal to PR over PQ. Sine alpha is equal to sine 90 minus theta, that is equal to PR over PQ. And therefore, cos theta is equal to sine 90 minus theta. Similarly, sine theta is equal to cos 90 minus theta. In general, the cosine of an angle is equal to the sine of its complementary angle. And so cos 50 is equal to sine 40, cos 0 is equal to sine 90, cos 30 is equal to sine 60, and so on and so on. Take an example. Sine x is equal to cos 72 degrees. Find x. Now x and 72 degrees are complementary, and so x plus 72 is equal to 90, and therefore x is 18 degrees. Another example. Cos x is equal to sine 5x. This means that x and 5x are complementary. X plus 5x is 90 degrees. 6x is 90 degrees and x is 15 degrees. Lastly, cos 90 minus theta is equal to sine 30. So 90 minus theta and 30 degrees are complementary. And so 90 minus theta plus 30 is equal to 90. 120 minus theta is 90. Minus theta is equal to minus 30, and theta is 30 degrees. Next, we look at the relationship between tangents, sines, and cosines. Now, consider this right-angled triangle PQR. In this figure, sine theta is equal to QR over PQ, and cos theta is equal to PR over PQ. Therefore, sine theta over cos theta is equal to QR over PQ divided by PR over PQ. That is equal to QR over PQ times PQ over PR. PQ cancels out, and that gives us QR over PR. Also, tan theta is equal to QR over PR, and therefore sin theta over cos theta is equal to tan theta. Tan alpha is equal to tan 90 minus theta, or tan 90 minus theta is equal to PR over QR. Multiplying these two tangents, we get tan alpha times tan 90 minus theta is equal to QR over PR times PR over QR, which gives us 1. And therefore tan theta times tan 90 minus theta is equal to 1. And therefore we say tan theta is equal to 1 over tan 90 minus theta. That is, the product of the tangent of an angle and the tangent of its complement is 1. For example, tan 30 is equal to 1 over tan 60, or rather you can say tan 30 times tan 60 is equal to 1. Next, trigonometric ratios of special angles. Let's look at the ratios for 30 degrees and 60 degrees. Now consider an equilateral triangle PQR of sides 2 units with a height PM. All the angles are 60 degrees. And so PM is a perpendicular bisector of QR, and therefore angle QPM is 30 degrees. In triangle PQM, using Pythagoras theorem, PM squared is equal to PQ squared minus QM squared. We've said that PM bisects the base QR, and so QM is equal to 1 unit. And therefore, PM squared is equal to 2 squared minus 1 squared, which is equal to 3. Therefore, PM is equal to root 3. Therefore, sin 60 is equal to PM over PQ, which is equal to root 3 over 2. Also, cos 30 is equal to PM over PQ, and that is equal to root 3 over 2. Cos 60 is equal to 1 over 2, and sin 30 is equal to 1 over 2. Similarly, tan 30 is equal to 1 over root 3, and tan 60 is equal to root 3. The ratio for 45 degrees. Now consider a right-angled triangle with two sides each of length 1 unit. Using Pythagoras theorem, BC squared is equal to AC squared plus AB squared. That is 1 squared plus 1 squared, and it gives us 2. And therefore BC is root 2. Therefore, sin 45 degrees is equal to 1 over root 2, opposite over hypotenuse. And cos 45 degrees is equal to 1 over root 2, adjacent over hypotenuse. But then tan theta we've seen is equal to sin theta over cos theta, and therefore tan 45 degrees is equal to sin 45 over cos 45. That gives us 1 over root 2 divided by 1 over root 2. Then we have 1 over root 2 times root 2 over 1, and that gives us 1. And if you go to the tables of tangents, you will find tan 45 is actually 1. We take an example. Given that sin theta is equal to 3 over 5 and cos theta is 4 over 5, find tan theta. In the solution, we know that sin theta over cos theta is equal to tan theta, and so 3 over 5 divided by 4 over 5 should give us tan theta. So we have 3 over 5 times 5 over 4, and that gives us 3 over 4. That is tan theta. Finally, logarithms of sines, cosines, and tangents. So far, when solving expressions involving trigonometric ratios, we have had to use the tables of trigonometric ratios and then the tables of logarithms. There are also tables of logarithms of sines, cosines, and tangents, which can be used to find the logarithms of these ratios directly. For example, find the value of cos 47 degrees times sin 24 degrees and 12 minutes. In the first method, we first find the cosine of 47 degrees, that is 0.6820. And then the sine of 24 degrees and 12 minutes is 0.4099. We then find the logarithm of these cosines. The log of 0.6820 is 1 bar 0.8338. The logarithm of 0.4099 is 1 bar 0.6127. We are multiplying, so we add the logarithm, and we shall get 1 bar 0.4465. Antilog of that is 0.2796. And so cos 47 degrees times sin 24 degrees and 12 minutes is equal to 0.2796. Now, the other alternative is to read the logarithms of sines and cosines directly from the tables of logarithms of sines and cosines. For example, we have number and the logarithm. Cos 47 degrees, the logarithm is 1 bar 0.8338. And then sin 24 degrees and 12 minutes, the logarithm is 1 bar 0.6127, and you realize the logarithms are the same. We add them and we have 1 bar 0.4465. The antilog of that is 0.2796.
applies course to course, it applies class to class. Miss a class, one class, maybe that's fine. Miss 2 or 3 for whatever reason, the rest of they're speaking a foreign language for you, and you just have to make it up, or going to class has no point. If you don't go to class, it just gets worse. It snowballs, and once it starts going downhill, you're in trouble. And so the biggest secret, or the biggest piece of advice, is get help early from as many people. And there's lots of sources for help, that other students in the course, teachers, etc. And so go there for it, and go early, and go as often as necessary.